Hi, welcome back to this video series on SMT solvers. Today I'm going to talk about a somewhat complex problem, how we can solve puzzles using SMT solvers. The problem is taken from a number theory book, but I will model it using SMT solvers and mechanically solve this instead of we humans solving it. Okay. I would also like to make a disclaimer that if it's a homework problem, please solve it using traditional math techniques rather than using SMT solvers. This is just a way to automate certain problem solving tasks, of course. Okay, so let's get into the problem. We have 4 men and a monkey. They spend a day gathering coconuts on a tropical island. After they have all gone to sleep at night, one of the men awakens and, not trusting the others, decides to take his share. Okay, so basically he silently wakes up and takes his share. Okay, he divides the coconuts into 4 equal piles because there are four men. It turned out that when you divide it like that, there was one remaining coconut, so he gives to the monkey. Okay, and then he hides his share. Basically no one will see that, and then he puts the other piles together and goes back to sleep. So each of the other men does the same. They don't trust the others, so they wake up. It turned out that every time they do that, there is one leftover coconut. Whenever they try to divide it by 4, they will have a remainder of 1. So in the morning, all the men awake, divide what's left on the left of the coconuts into 4. Again, there is one left over that is given to the monkey. Find the minimum number of coconuts that could have been in the original pile. That's the question. The question is, find the number of coconuts that could have been in the original pile. Okay, so this problem can be solved using traditional math techniques. For example, using linear Diophantine equations. I will just quickly model that first to convince yourself you can use traditional math techniques, and then I will automate this using SMT solver. Okay, so for example, how do we model this problem if we are solving through just traditional math techniques? Okay, let's assume we have x coconuts to start with, right? Let's assume x is greater than or equal to 0 because the number of coconuts greater than or equal to 0 makes sense. Okay, what is the first thing the first person does? He wakes up in the night, right? He divides this x by 4. While he was doing it, he found out that there is one remainder. Essentially, it means to say the first person takes away x minus 1 by 4, right? This must be perfectly divisible by 4. Okay, so what is left over then? The leftover is x minus of x minus 1 by 4, which means I'm going to say like this. Initially we have let's call it R0 to show a reminder, right? Initially we have x items, x coconuts. After the first person silently awakens, he took his share, right? So what is left over then? It must be x minus of this, right? Okay, what is x minus of this? Which is, you can easily see that you are subtracting x from x minus 1 by 4, which is nothing but 3 by 4 of x minus 1. Okay, so let me clarify this once. We have x coconuts. The first person took x minus 1 by 4 away, right? So what is left for on the pile? Okay, so remember 1 is given to the monkey, so we have x minus 1. That person took away his share. Okay, first person took away his share. That means you are left with, if you simplify this problem, you are left with 3 by 4 of x minus 1. Okay, that's basically what I wrote here on my left hand side. Okay, all right, so this is basically the idea. All right, and what I'm going to do is I'm going to continue this process, right? What is the second person going to do? He's going to wake up. He does the same trick, right? He's going to say, I will take my share. And the problem statement says every time they do, they're left with 1 extra coconut that they gave it to monkey, which must be happy, I guess. So, and then we'll have R3. What is R3? R3 is also like the same structure. The third person wakes up, he takes his share, and whatever is left over now is R2 minus 1. Okay. So let me just finish this. The last equation is R4, right? R4 will be, after the fourth person wakes up, what will be the leftover? The leftover will be this. This is how I model this problem. And now you can see that R4 is a function of R3, R3 is a function of R2, R1 is a function of R0. So you should be able to rewrite everything in terms of X, meaning R4 can be rewritten as a function of X, right? The problem statement also said that after the fourth person took his share, okay, when they tried to divide the remaining share, which is R4 by 4, they saw one extra coconut, right? What it means is that R4 is basically, remember R4 means after the fourth person took his share, the leftover, that's the final pile they see in the morning, can be written as 4 times some y, which we don't care exactly. So this is basically it, because R4, because the problem statement said that there is one left over when they divide it by 4. Okay, so this is a linear differential equation which we can solve it. I have talked about how to solve linear differential equation in my other videos. Differential, I think. I don't really know how to pronounce his name properly. Linear differential. This is basically the idea. But anyway, I did substitute all of these and replaced R3 by R2 or R2 by R1 and so on, and got an equation like this: 81x plus 1024y is equal to 781. Okay, this is the equation I got after writing all of these one by one, right? I replaced R3 by 4 of R2 minus R1, and then I did this direction, and then this, all the way here. Okay, that's the reason why I got R4, right, in terms of X and Y's. Okay, so R4 will be a function of X, of course, and then you already have this 4y sticking as a plus, but there are fractions coming. That's why you see this portion contributing 1024. Okay, so the goal is to find an X greater than or equal to 0, and differential equation will help you to solve this problem. Okay, so this is the human traditional math technique. It's a little bit painful to solve this equation because you have to take GCD and you have to apply extended Euclidean algorithm and all of those, but eventually you'll be able to solve it and find the answer. If you just take your time, it's just a lot of work to do, but it is not difficult once you model the problem. Remember, R0 means what is left over after somebody took it away. Initially, X is left over, right? R1 is after the first person took it away, what is left over. R4 means after all the 4 people took their own shares independently, not stealing others, that's the leftover. And then in the morning, they will take R4, divide it by 4 parts, and then they take they found out that there was one left over, and that's basically the reason why I have this equation. Okay. Anyway, so I'm now going to show you how I model this using SMT solver. The goal is to find the smallest X, by the way. The X is the number of coconuts. Okay. How do we find the smallest number of coconuts that satisfy this equation? Okay, so this number of coconuts has to be small, minimum, least. Okay, that's what we are trying to do. So let me show you how we can solve that problem. So I modeled it using Z3 solver, right? And here is the model of the C3 program. It's exactly the same as what I explained it on my whiteboard. I have made it parameterized, so the model looks a little bit more abstract than actual numbers. So I assume there are 4 Saylor. That's basically the problem statement, right? X is the number of coconuts, right? X is the number of coconuts. Number of coconuts. Okay. So what are we trying to do? We are trying to optimize this value X. That's the reason why we are using the optimization capability of SMT solver. And we are looking for a positive, to be more precise, non-negative value for X. Okay. So the way I modeled it is this. I created an array, right? Number of coconut is an array. Remember, there is a state, right? The first person wakes up, he takes his share, throws away the one left over to the monkey, and then the second person does that, third person does that. So we could easily abstract that into a more cohesive code. So this is what I did. So I have an array called number of coconuts array. Initially, we have X in the first position, right? Index starts with 0. So we have X coconuts left. Remember, the problem statement said that when X was divided by 4, there was 1 left over. That's basically the reason for this statement. Percentage means modulus, right? Leftover is 1. And then the next statement says that, I mean, each of the sailor does the same, right? The next sailor wakes up, he does that. Third one does that, fourth one does that. So I wrote a little for loop that basically models each of those things that we saw on our whiteboard. Basically takes the current share, subtracts it by 1, divided by 4. 4 is the number of sailor, okay? And that's the reason why you're seeing a number of sailor minus 1, which is 3 by 4 on the whiteboard, okay? You can easily change the number of sailor to 5 and so on. But anyway, this is basically it. And the problem statement also said that there is always a remainder of 1 whenever they try to divide the number of coconuts that are left over there, okay? A number of coconuts that is left over there, okay? Okay, so, and then we ask the solver, find out the solution. If you find the solution, print me the number of coconut. By the way, this is not that simple problem to solve using a SMT solver, but I got it run. It took some time when I was running for 5 sailors. The solution was 15,621. I ran it for 4, which is much quicker than 4 sailors. So I will now show you the run from my execution, okay? And I will also show you some more details that you could use when you are developing similar, solving similar problems using SMT solver. It will take a couple of minutes. It was really slow for 15,621, the other scenario where there are 5 sailors. I'm not claiming my model is perfectly done. Maybe there are some optimization tweaks, but at this point, the emphasis is on how do you model sort of recursive dependencies, if you will, among the variables. Very simple. You can create a state variable, which in this case is an array. We model the different states using array indexes, right? And then we model the dependencies among the number of coconuts left over after each person silently steals is part of the share. So that was easy to model. Okay, so it should come up now very quickly. Okay, it turned out that I didn't know this story, by the way. It turned out that this particular problem is sort of well known in math puzzles space. When I was looking at online materials, I saw that people were solving many variants of this problem. Okay, they were talking about 5 sailors, and then they were talking about the last, when they wake up in the morning, they don't have 1 left over, right? Everybody can equally divide it. That kind of different variants were there. But anyway, but the spirit of the problem is the same as what I am showing you today. Okay, so the minimum number of coconut must be 1021, which you can confirm yourself, right? The first person wakes up, 1021 is clearly not divided by 4. He will throw the 1. So he will see 1020, and 1020 will be divided by 4, and he will take his share. And then this next person will continue the next part, and so on. So this is basically it. Okay. So this is the minimum number of coconut we needed. So we can also actually use some of the features of SMT solver to print the intermediate model. Okay. So we can say, let's print the simplified expression for, I'm going to do this inside a loop. Okay. So we can see it for every simplify the number of coconut for I. Okay. So we do know when I is 0, the number of coconut is X. So let's see the expression for other men. Okay. 1, 2, 3. When they took it, what is the mathematical expression we are having? So we can print it. Okay. So let's print this and see what happens. Yeah, you can see here if you write everything in terms of x, you have equations like this. This is clear, hopefully, from my whiteboard when I explained that you start with the x and then you subtract away x minus 1 by 4. So you're left with the 3 by 4 of x minus 1, right? So that's what you're seeing as part of the expressions here. Okay, if you take the 3 common, you will see what I mean. 3x minus 1 by 4 you will get from here, and then the last part is this is the part that shows in the morning when they wake up. This is the expression they have to solve, essentially. Divided by 4, they get a remainder 1, and then this is what the SMT solver is actually solving this for us. Okay, so it found 1021 is the minimum value for x to satisfy this equation. Okay, it was quite fascinating for me to solve this using SMT solver. Let me summarize what we learned. We said that we can configure the number of Sailor to whatever number we like, 4, 5, or not. There is some limit, of course, computational limit, because the number of variables that you're solving will become huge for an SMT solver. We are using the optimization engine. We are asking to come up with the minimum value for x. X is the number of coconuts. And then this particular plot comes from the problem statement that says when they divide it by 4, number of Sailor is 4 in our case, they get a remainder of 1 at the beginning, right? And then in every step, they have the same property. That's why you see the same property here, okay? For every state, you see the same property. And then we ask the solver to solve and give us a minimum value for x. All right, that's basically it, how to use SMT solver to solve an optimization problem, which could be, of course, very well solved with the help of linear differential equations, but it's more involved, a lot of computations, manual calculations you have to do, of course. All right, thank you.